Hi, everyone. Good afternoon, or good morning, or good evening, depending on the time zone that you're joining us from. My name is Irina Enake. I'm the marketing project manager for Technobiz, and I will be the host for today's webinar. With me, I have Professor Elena Simone from Politecnico di Torino. She's our guest speaker for today's webinar on a very delicious topic, called a crystal engineering approach to tailor functional properties of food formulations. Before I introduce Elena and let her take the stage, I just wanted to tell you a few technical details about the webinar. We will aim to keep the webinar within 30 to 45 minutes. We will record it, so it will be available on our website tomorrow. You will receive a link, so you can also watch it at another time. The audience is muted, but at any time during this webinar, you can send your questions in the Q&A chat. And at the end of the webinar, we will read the questions out loud and try to answer them. And if any questions come to mind after the webinar, that's perfectly fine. Just write to us to info@crystallizationsystems.com, and we will try to answer or pass the questions to Elena if that's the case. I noticed quite a few new names in the audience for this webinar. So I just wanted to take a few minutes to introduce Technobiz. So who we are, what do we do? So we are a Dutch-based company in the northern part of the Netherlands, in Alkmaar. And we manufacture laboratory technology dedicated to solid-state research, formulation, and process development. And as of recently, also for chemical synthesis. So we serve two different areas. One of them is chemists working in crystallization screening. So that we've been doing for many years already with the crystal breeder, crystal 16, and crystalline. And as of last year, we're also supporting chemists working in process chemistry with the Reactol, which is dedicated to reaction screening. So from the crystallization screening portfolio, I think many of you in the audience will be familiar with the crystal 60. That's our most popular instrument, and it's an ideal tool for measuring solubility, metastable zone width determination, phase diagrams, polymorph screening, and so on. But we also have crystal breeder, which is dedicated to single crystal growth, and the crystalline, which is the instrument that has advanced cameras. So it really helps chemists to visualize their entire crystallization process. So think of particle size, shape, and distribution. It's an ideal tool for that. And with the Reactol, like I mentioned, this one is new in our portfolio. This is a multiple reactor system, 5 reactors to be specific, with automated dosing, sampling, quench and dilutes. So it really helps chemists to accelerate their chemical synthesis. So for those working in route scouting, reaction screening, reaction optimization, profiling, and kinetics, we designed the instrument for these type of chemists in mind. That's about it from the introduction side of the Technobiz. I'm really excited to have Elena with us today for the webinar. So Elena is currently a full professor at Politecnico di Torino. She has extensive research in chemical engineering, specifically in food formulation. She earned her bachelor's and master's degree at the University of Pisa, and then she moved to the UK for a number of years, where she completed her PhD at Loughborough University. She also worked for Unilever R&D in the UK. Yeah, and I'm really excited to have her here because last year I had a chance to listen to Elena. She was a guest speaker at a workshop that we organized in Torino on the same topic that she's presenting today, but today she even has new insights, and I really, really liked it. So when I said that it was a delicious talk, I mean it. So yeah, I hope everyone will enjoy it. Yeah, I think that's it from my side. I will stop sharing my screen. And then Elena, please go ahead and yeah, share your presentation.
Yeah, thanks, Irina, for the very nice introduction. Yeah, for those who were at the meeting in September, I've seen a few familiar names. I have new results, so hopefully you can see something new. And let me just share my screen. Okay. Yeah, so Irina, can you confirm that I'm sharing in presentation mode?
Yes, it's in presentation mode. All good.
Okay, thank you so much. So yes, good afternoon or good morning to all the attendees. What I'm going to present today are a few ways to apply crystal engineering to food science and food formulation. So my talk is divided into two different parts. One more focus on a specific topic called Pickering formulation, and the other ones is on the design of triglyceride mixture for confectionery product. So just to start, I just want to give a little bit of definition of multiphase and food formulation. So in order to create different textures and different mouthfeels, what you can do when you prepare food is to create multiphase materials, so to incorporate air bubbles or water droplet in an emulsion. So here there are some examples. Ice cream is a very interesting structure where we have air bubbles that provide the characteristic softness of the material. Same with whipped cream or butter. Again, is an emulsion whose spreadability depends also on the size of the small water droplets incorporated in the material. So multiphase formulation are really widely common in food, and they are really used to create different mouthfeel, different perception of food. Now, the problem with emulsions or foams is that they are made of two immiscible phases, so they are thermodynamically unstable and they can separate over time. So what we can do is we can try and stabilize them either using surfactants, which is the usual strategies, or we can use solid particles, and this is called Pickering effect. Now, compared to surfactants, solid particles are very strongly absorbed at interfaces, so they provide quite stable formulations. Sorry, I need to. My cat was bothering me a little bit. Pickering particles are solid particles that provide very stable formulation, and depending on the nature of the particle, we can stabilize an oil in water or a water in oil. So if we look at the absorption energy, so how strongly a particle can absorb at an interface and provide stabilization to a structure, we can see that this depends on the size of the particles and also on the three-phase contact angle, which is basically how hydrophilic or hydrophobic is the nature of my particles. So hydrophilic particles would be more suitable to stabilize oil in water. Hydrophobic would be more suitable to stabilize water in oil. Also, what we need to take into account is the thermodynamic stabilities of our particles. So they have to be thermodynamically stable in the formulation, and also they have to be insoluble. So they shouldn't dissolve in either of the phase. Now, we can use crystalline particles as Pickering stabilizer, and the crystalline particles are faceted, so they are characterized by a an intrinsic anisotropy, which depends on the crystal structure. So depending on the crystal structure, we will have different parts of the atoms or the molecules on each different facets. So we will have different surface, different chemical nature and different wettability, hydrophilicity or hydrophobicity on the different facet. Now, this has been shown a while ago by Jerry Yang at Imperial, that measure the water contact angles, so how hydrophilic were different facets of paracetamol form 1. So we can see that different facets show different wettability because of the different groups of paracetamol that are characterizing each facet. If we change polymorph, we can also see different surface nature, and then again, different molecules also show anisotropicity. Now, because like I design crystals, I define myself as a crystal engineer. I can actually use this anisotropy if I am able to understand well how surface properties are related to crystal structure to actually design particles. So crystal engineering can be really like a way to exploit this crystal anisotropy and find the polymorphs and the shape that is better suited for a specific formulation. So whether I want water in oil or in water, or depending also on the type of oil and the nature of my aqueous solution, so the pH, for example. Now, surface properties are important not just for food formulation, but also in general for many downstream operations. So the chemical surface nature, the roughness will affect how particles interact with each other. So if it's easy for them to stick to each other, or they will affect flowability. So surface properties will also affect unit operations such as, again, compaction, granulations, and so on. So understanding how crystal structure affect surface properties is useful also for other industrial sector rather than the food one. Now, because I'm interested in food formulation, I decided to work with a specific series of compounds that are of interest for the food industry, but also that are quite rich in terms of the polymorphic and the solid state landscape. So what you will see that I will show you are some examples using polyphenol molecules, so quercetin and curcumin, but we've been working on xanthan as well. And then so polyphenol molecules, again, they can form co-crystals, they have many polymers, so there are a lot of opportunities to play with different solid forms for to tailor anisotropic surface properties. And then another class of compounds that I'm quite interested in are lipids, so triglycerides. They don't necessarily have health benefits like the polyphenols. However, those are an essential macronutrients, and they are already an ingredient in food. So we can really play with engineering tags and crystals to manipulate the texture and mouthfeel of food. Another thing that I'm interested in is getting this material from agri-food residues. So again, there are many challenges related to this, especially in terms of purities, but we're trying to work also on the source of this material. So the first thing that we try to do using quercetin as model compound, in this case, we took as model structure a solvate of quercetin and DMF. DMF not specifically suited for food formulation, but it was the model compound that we had at the time. So just please just look at it as a model compound. And what we tried to do in collaboration with the Cambridge Crystallographic Data Center was to develop a workflow, a methodology using a series of their particle informatics tool to understand how crystal structure affects particle quality attributes. So again, wettability, surface roughness, facet-specific chemistry, and so on. So we started from the crystal structure of our solvate, and then we did, well, first of all, we just look at the structure. This is normally quite useful also to see how the molecules are arranged. And then we did a bulk intrinsic symptom analysis. So we calculated the main intermolecular and intramolecular interaction among within a specific volume of our crystal structure. Then we applied the attachment energy model, which basically kind of like ranks or give us which specific symptom contributes to the growth of the different facets. So then we can understand a little bit the nature of the different facets, so whether they grow via hydrogen bonds or pi-pi stacking and so on. So with these particle informatic tools, the type of data that we get are, again, a list of intermolecular interaction within the bulk crystal lattice, where we can separate and rank them based on their type. So whether it's a hydrogen bond or again a non-polar interaction, then we can measure the strength and the directionality. The directionality is then used again through the attachment energy model to calculate facet-specific intermolecular interaction, so how a specific facet is growing, to calculate the topology, so basically to get some roughness, atomic roughness maps of the facets, and then to understand the facet-specific chemistry, so what parts of the molecules characterize each facet. And those information tells us a lot, again, on the facet-specific roughness, which can affect sticking probability and also flowability. We can get some information on the surface anisotropy and the relative hydrophilicity of the different facets, and also we can get some information on the desolvation behavior. So, for example, if we see that one facet is dominated by the solvate molecule, perhaps this is going to be the facets where it's easier for them to leave the structure. So if we maximize these facets, probably we might have a problem with stability. So again, the first thing that we did, we analyzed the different interaction. And as we can see here, when looking at the first 5 interactions that characterize the crystal lattice, we cover over 75% of the total lattice energy. So those are 5 interactions which are fairly good representative of the nature of the crystal lattice. And we can see that they are hydrogen bonds. Okay, so polar interaction between quercetin molecule and quercetin DMF molecules, but we also have relatively equal contribution of offset stacking interaction. So we can see that already in terms of interaction, we are roughly maybe equally distributed or with slightly higher percentages of hydrogen bond compared to offset stacking, but we can see already that there are different types of interaction, which might indicate that our surface will be anisotropic. So, and again, this is maybe a bit crowded, but what we've done is we grew a crystal using the crystal breeder. we index it to try and understand the facets that we could actually obtain experimentally and measure. And then using the attachment energy model, we created these maps. So those are the facets where we can see the rugosity of the facets, both from the top view and from the side. So we can see differences in the roughness based on, again, the position of the quercetin molecule, the DMF molecule, compared to the plane of the facets. And then in different colors, we can also highlight the presence of hydrogen bond donors and acceptor, which are the red and blue parts, and then the aromatic kind of like bonds, which are those orange parts. So we can also formally calculate, again, as you can see here in this table, for each facet, the area, let's say, occupied by the different types of atoms. So we can see, for example, that this large facet here is very much exposing DMF molecules, while these other two are a little bit more occupied by the aromatic molecules, which, if we look at facet 001 and 200, are in two very different positions. So facet 200, we can see these quercetin molecules, so those are the aromatic rings, which are almost vertically positioned compared to the facet, while those are a lot flatter in facet 002, and they are a little bit hidden within the structure in facet 1-1, 0. So we try to do some experimental validation. We try with SEM, where we can see here the 200 facet, so the one with kind of like the vertical quercetin molecule, which is relatively rough, as you can see, compared to the 1-1, which was, again, relatively rough, but it wasn't really like exposing those vertical molecules. So this was, you know, like, we have to consider that the scales are different from the simulation and the SEM, but at least the differences that we can see were somehow in agreement with the simulation. We also did contact angle measurements, so single facet contact angle on the lateral ones, and we saw that they both are hydrophilics, and those are the ones which are where the hydrogen bonds are present. And then we tried to do some atomic force microscopy, especially on these large facet over here, which, if you remember, is the one that shows quite a lot, that exposes quite a lot of DMF molecules. And what we saw was very interesting, because over time we start seeing these holes. So those are, again, like channel that are formed through desolvation. So this also was not very expected, because it kind of like ruined a little bit our AFM measurements, but it was very in nice agreement with the simulation that show that, again, we have preferential desolvation on this DMF facet. We thought that this was really still not enough in terms of trying and see differences between facets. So we also look at spectroscopic techniques to analyze each facets. Instead of using bulk ATR IR, which is kind of like doesn't have the resolution to look at different facets, we went to the electrosynchrotronetry assay, and we tried this optical photothermal infrared spectroscopy microscope. So this is not the same resolution as a nano IR, but is a lot higher spatial resolution compared to a normal IR microscope. So here we could really look at the different facets, freshly cleaved, and then over time. And as you can see, so those are all normalized data. They are averaged on different points of the same facets and of different crystals. And you can see that there are quite a lot of differences among the different facets. So we're still kind of like analyzing this data, but we saw that the main differences are related to the CH bending modes, especially the out of plane and in plane ones. So if you remember this facet 001, this kind of like purple line was the one with the flat aromatic rings of quercetin, while the other two were in the other two the quercetin molecules were a little bit like more vertical. So being more vertical, those out of plane CH bending modes seems to be more favor compared to the in-plane bending, which instead is a lot higher intensity on the kind of like facet with the flat aromatic rings. So there are differences really related, especially on the different position of the aromatic rings of the quercetin molecule. So this was very nice to see that we could actually detect differences and show that, again, we could see an isotropy in terms of chemistry. Then kind of like linking these directly with the modeling, something that we are working on, because again, it's not that easy. We also try nano IR. So on the same kind of like facets, we basically we did AFM combined with IR. So we get basically an IR spectra of a point on a surface of the crystal with the same resolution of AFM. This one, to be honest, didn't work so well. So you can see that this is our 001 facet, so the capping facet, the one with the OH groups, and this is the 1-1 0. So the large one with the DMF molecules. There are some differences, but especially for the 001 facets, we can see quite a lot of dishomogeneity on the facets, and this might be due to the fact that when we try to cleave this facet, we don't get a clear kind of like cut, but we always get a very rough surface, which seems maybe like counterintuitive, because when we look at the modeling, this is kind of like flat surface. However, perhaps what happens is those are kind of like stronger offset stacking interaction. So when we try and break in that direction, we have somehow sort of like fragile fracture, which determines this roughness. So again, we're still looking at this data, but nano IR really depends a lot on the quality of the surface. If the surface is not very flat, the quality of the IR images is not as good as what we got again from the OpTIR. So then we've done this work for quercetin, and with another PhD student of mine, we're also looking at actually making this Pickering formulation, so making the particles and then making the formulation. Now, my other student, Julia, she's working on curcumin. Curcumin is very difficult to find pure, so we're working with a mixture of different similar molecules, which are, however, fully miscible. So we get solid solution, the structure is the same, so the properties should not change too much if we change, you know, if we include an impurity. We look at two different polymers, form 1 and form 3. So form 1 is the stable one, form 3 is metastable. However, it's very kinetically stable. So if we put it in ambient temperature, in ambient condition, or also in suspension in water, it doesn't really like convert very quickly to form 1. So it stays there for like months, years, and so on. What we noticed was that so we did the same kind of like analysis that we did for quercetin DMF, and form 3 was significantly rougher compared to form 1, and also all the different facets were exposing more frequently OH groups. So we thought, okay, maybe this form 3 is a little bit more hydrophilic. And indeed, when we actually look at the contact angle, we found that form 3 was a little bit more hydrophilic compared to form 1. So it's still not hydrophilic enough to stabilize oil in water. So we could only work with the water in oil emulsions, but still we could see some differences when making these emulsions. So the first thing that we needed to do was to find a procedure to make these particles at, you know, like micron size, which is suitable for food formulation. So we did reverse anti-solvent crystallization. So we had our solution of curcumin in ethanol, put it in a big beaker of water, and then mix very quickly to create uniform supersaturation very fast and get relatively uniform size and shape distribution of form 1 and form 3. For form 1, we had to add a little bit of seeds of form 1, so we did seeded anti-solvent. And we got two different polymers with very similar shape and size distribution. And then we prepared these emulsions. So those that you see are water in oil emulsion. What is very nice already is that the two polymers have different colors. So form 1 is yellow, form 3 is orange. So even from the point of view of using natural colorants, we can use different polymers. So this can be quite useful. And then again, Julia, now she's at the University of Leeds with a collaborator of mine in the physics department, Dr. Poncevic, and we're using light sheet microscopy to kind of like look at the position of the crystals at the interface. So form 3, as you can see, has a very nice affinity to the interface, also related to that kind of like specific contact angle. For form 1, now the image is not clear because what we think is happening is that some of the form 1 crystals are staying in the continuous phase. So this is more hydrophobic. So those particles tend to stay a little bit more in the oil rather than the interface. And this means disappointingly like worse images, but also slightly worse stability of this form 1 emulsion, although they could still stay for quite long, several months, nicely separated with the two phases. Now, by playing with the concentration of water and the percentage of particles, we can get different size distribution of the water droplets, so we can get different textures in the food. More particles and more water also determines smaller droplets. And as you can see, in general, with form 3, which is slightly better stabilizer, with the same condition, we get slightly smaller droplets, smaller and a little bit more stable. So just to conclude this first part, and then maybe I'll just go very quickly to the second, I show you how we can really use crystal engineering to formulate Pickering formulation. And I think the knowledge that is needed, which is a good knowledge of the relationship between crystal structure and surface properties and anisotropy, can be useful also for other fields. And we have very interesting tool, but we need to do a little bit more in terms of experimental validation and try to kind of like link, especially like different scales of simulation. So then I just want to show you quickly some of the work that we've been doing on fats. So edible fats are mixtures of triglycerides, which are molecules characterized by a glycerol backbone and 3 different fatty acids. Those they can vary in chain length and level of saturation. And again, depending on the type of fats that you are working with and the origin. So, for example, if it's milk fat from cow or from buffalo, we will get different tags composition. Now, I got really interested in this topic, especially because one of the kind of like the classical example of fat crystal, which is cocoa butter, which is known because it has different polymorphs. Cocoa butter price is increasing very steadily. So if we want to keep, eating and buying chocolate, we need to somehow start to find different fat sources. Which resemble somehow the texture and crystal properties of cocoa butter. So I started to work with the so-called cocoa butter equivalents, which are mixtures of fats of different origin compared to cocoa butter that can still be used in chocolate. Now, because they have a different tags composition, what I was trying to understand is the relationship between composition, tags composition, and crystallization behavior. Mixture of triglycerides can form different polymorphs. So the three main polymorphs of triglycerides are the hexagonal alpha, the orthorhombic beta prime, and the beta. So this is the subcell, so the short range order. Then if we look at our tags crystals, let's say from the side, we can also see a different type of stacking. So the way that molecules are actually arranged close to each other. So we can have a 2L stacking, 3L stacking, or again, this is 4L and so on. So every mixtures of tags or pure tags will have a specific subcell, a specific combination of subcell and type of stacking. So we can see 2L alpha forms, 2L beta prime forms, 3L beta, again, depending on the structure of the molecule. Cocoa butter, chocolate has 6 different polymers, which are all, again, a combination of different type of stacking and subcell. What we want is form 5, which is a beta polymorph with a 3L despacing, lamellar spacing. Again, I'll go through this quite quickly because I'm sure like many of you will know how X-ray works, so we can use this technique to look at both the short range order, so you're looking at the wide angle, so the kind of like large scattering, but for the long range order, we can look at the so-called small angle X-ray scattering, so those small scattering angle which characterize larger structure. And these are some examples of polymorphs of tags. So this is the Sachs region and the wax region of an alpha polymorph. So an hexagonal subcell has only one peak in the wax region. And then in the Sachs region, we can see a series of equally spaced peaks. And again, if we plot their position, so the scattering vector as a function of the order of reflection, we get a line, and the slope of this line is exactly that despacing. So how big is the lamella of our structure? So this is an alpha polymorph. Beta prime polymorphs has, like very similar kind of like Sachs pattern, so slightly different slope. And the wax fingerprint is characteristic of an orthorhombic form. And then again, a monoclinic form for the beta. So the Sachs region can be used, for example, to check how many phases are present in my sample, because I will have as many phases as many lines I can draw. These are again example of cocoa butter and the milk fat. So cocoa butter at equilibrium has a beta polymorphs in a 3L form, but we can see here an extra phase here, which means that there is another phase. This is probably like very saturated triglycerides, which are separating from the main polymorph. Milk fat is characterized by a beta prime and an alpha mixture, and as you can see, the solid fat content is a lot lower. So we have this broad kind of like scattering peak, which is related to the presence of liquid tags. Again, from the position of these peaks, we can get the lamellar spacing. So I've, like tried to look at many different cocoa butter equivalents. I'm not going to show you too much in details here, but if we only look, at the Sachs region, where we can see, like the presence of the different phases, we can see that we always have the characteristic polymorph of chocolate and then extra phases. And those can be a problem when we start mixing in a formulation, because they are a little bit unpredictable, especially in terms of stability. So again, we measure, like many different composition, and they are all kind of like different to the point that still it's a little bit unclear exactly the correlation with the tags composition and the presence of these phases. So we're really working on a more rigorous thermodynamic approach, perhaps incorporated some machine learning elements. I'll just again go quickly with some fat replacers. So again, as you can see here, different composition, different polymorphic landscape. And again, it can be a problem when you are trying to formulate a product. And here, basically, what I've done is just mix cocoa butter and a little bit of our milk fat replacer, and we can see again different phases. Although the main one is still the desired form 5-1, but we still have these other crystals, which again may come out, for example, causing blooming. So yes, I think I'm sorry for going a bit fast in this second part, but hopefully if you have some question, yes, feel free to ask. But I just wanted to show you a little bit some other issue related to lipid crystallization, food crystallization, which perhaps if you are not really in that field, you might not know. And also, like, I wanted to put it into context of where we are going, because again, with the depletion of cocoa butter increasing in price for different reasons, we will need to kind of like look for different sources of fats, also from waste, maybe. And it's really advisable to have some strong knowledge of the crystallization behavior depending on the composition. So just want to thank my group and collaborator, and to thank you for your attention again. If you have some specific question, maybe on the second part that I went a little bit far, feel free to ask or send Irina an email, and we can be in touch. So for now, thank you for your attention, and yeah, happy to answer any question.
Thank you, Elena. That was very interesting. I definitely know what I'll be doing this evening. Go to the supermarket and buy some chocolates.
That's an excellent idea.
Always. So thank you very much for sharing your insights with us. I'm really excited that we could bring your research also to a wider audience today, since last year, since Torino. So for everyone, you can send your questions in the Q&A, and then we will try to answer them. I can start with the question for you, Elena, because you mentioned you use crystal breather in your research. I don't know if you use crystal 16 as well.
Yes, so we have both, and crystal breeder is very nice to grow big crystals, and especially because we need to do this kind of like facet specific measurements, so we need relatively large crystals, and with the breeder we've been trying evaporation, cooling without agitation. For the crystal 16, we use it quite a lot for slurry experiments.
Yeah.
So if we want to make co-crystals, or if we want to look at relative stability, so for example, that form 1 to form 3, to check that it was not converting, we put slurries in water and just like, you know, like steer them for a long time. With fats also, we did some work with the breeder, looking at the crystallization and melting point, especially, you know, like if you don't have a lot of material, that can be quite useful, and you get information which are comparable with DSC, and you can recover the sample. So we're using both, in my lab.
Yeah. Thanks. I think that answers my question. I was curious what you thought the added benefit for you was, and where was it helpful to support the research that you just presented. So thank you for that. So we have a question in the chat related to slide 7. Which software did you use for the energy? I don't remember what was on slide 7, but
yeah, no, it's so we use Mercury, and again, so the Cambridge Crystallography Data Center Mercury. There are several options. There is there is a series of tools called I think it's CSD Particle and Visual Habit, where you can do all this calculation. Now, I think some of the calculation that we've done, we, together with the Cambridge Crystallography Data Center, we wrote our own script in Python, and you can implement. I can send the publication because we also publish the code, but usually CCDC, they are very helpful. So if you need help with there's a lot of material online if you want to learn how to use this tool, and they're really helpful in terms of like helping you with this calculation. But yes, we did with the Mercury, and we did maybe like some structure optimization with the Material Studio. But apart from that, it's in Mercury. The work is published, so maybe I can show again the reference, and you can find all the details in there in this paper here. Just show it again. So this Prandini et al. On powder technology, which we published last year. So this is all the methodology and some of the scripts that we have implemented with CCDC.
Yeah, thank you for sharing that, Elena. Then we have another question. Thank you very much. On the stabilization mechanism, do you have an idea of the actual occupation needed of the interface by crystals? Pictures look as if it is fully covered by crystals.
For the pickering,
I assume.
Yes, that's an interesting question, because the level of coverage depends a lot on how much water you have, and then the amount of crystals that you have. Of course, you know, the more crystals you have, and the more interface you will stabilize. So with the same volume of water, you'll get smaller droplets. And also, you know, like increasing the water amount, you can see kind of like smaller droplets, because again, you have a bit more surface area available. But so it's an interface in interplay between these two, kind of like volume of water and the amount of particles. So the covering really depends. So there are other, maybe I can show you other picture. I don't know if I'm still sharing my screen, but there are other cases where larger droplets are a lot less covered. So for example, these ones here. Yeah, so with less particles, you see, especially with high amount of water, like lower coverage. But then those might be a little bit less unstable because they will tend to coalesce a lot more.
Yeah. All right. Then we also have a question on what is the effect of the relative intensity in the X-ray diffraction pattern on particle shape or morphology? Is there any correlation between difference in relative intensity and particle morphology?
So when we do we normally, so I'm lucky that in my group there is a very good crystallographer from single crystal. So we use single crystal to solve structures. We shouldn't really see kind of like any effect of shape in the XRD, and then we do the indexing. Of course, if you do powder XRD, then you might have an effect of shape and morphology because of preferential orientation, and then like those needles will be more likely fall flat on their facets, so you will see difference in intensity. But like when we solve the structure, we normally do that from hopefully from single crystal. Now XRD, or now we're trying something with some collaborators in IIT in Pisa with electron diffraction, but normally we don't have that problem. Yeah. Hopefully I answered the question.
If anyone wants a clarification on that, just feel free to send the question in the chat. I'll move on to the next question. Thanks for the nice talk, Elena. I have a question regarding your nano AR study. So depending on the crystal growth mechanism, for example, spiral growth, can there be steps and ink structures on the crystal surface? Do you think they can affect the spectroscopy results?
Yeah, thanks, thanks, Sandil. There might be. So we cleave them. So hopefully we we see the cleaved surface, which is fresh, so we don't have too much that kind of like effect of the growth mechanisms. But I think for the nano IR, you would see differences. For the optier instead, this will be like a little bit more average. So in that case, the rugosity is kind of like less affecting our measurements. So I thought that to do that kind of measurement, I really needed nano IR because I really needed the resolution. But actually, something in between, like optier, was a little bit better because it was less dependent on the nature of the surface. So I think they will affect, and that's what we saw in the nano IR. But with the other technique, it's a little bit better. Yeah.
All right, and then I think we have a couple of other questions coming in just now. So one of them is it an option to promote growth of specific facets of a polymorph to improve its interfacial properties for the Pickering effect?
Where do you see these questions? Sorry, Rina.
I think they just came in.
Okay. To promote growth of specific polymers, so to improve its. Yeah, well, I mean, I hope that's exactly the point. So we kind of like maybe like choose a solvent, and this is something else that we're doing. So looking at interaction between facet and solvent that increase the specific facet or another to again like having a specific interfacial properties. So we choose the polymorph, then we choose the habit, and then if we're good at designing the process, we can really like have a good control of the surface chemistry. So I think that again is one of the strategies that can be used to control surface properties.
All right. I see a couple of questions still in, but I'm also conscious of the timing that we are approaching the 1 hour. So, Elena, I will pass you the remaining questions, and then maybe together we can answer them. But I just want to keep things within the allocated time. If you have any further questions, you can send them through the chat, or you can send them to info@crystallizationsystems.com, and we will get back to you. Elena, I want to thank you so much for your time and for the insights that you shared. It was a pleasure having you. We look forward to see what you are working on next. And I think indeed the supermarkets will have an increase in the chocolate purchase today.
But no, don't buy too much, because there's not too much cocoa butter left. No, thanks for the invitation, and thank you all the attendees for listening to me, like blabbing for 45 minutes. I hope you enjoy. Yeah.
And thank you everyone else for joining. The webinar will be available tomorrow on our website. And thank you for joining. Enjoy your chocolates, and have a nice evening. And thank you, Elena.
Thank you. Bye.
Ciao, ciao.